So let me start with a quick backup. So I think last time we started talking about electric field, and we defined it as being the force, electric force per unit charge. And we also talk about electric field lines like this, positive, and like this for negative. And we talk about superposition. We, I think, solved some examples. And we talked about calculation of electric field for a continuum, for a continuous charge distribution. And I think we solved a couple of problems. And for example, this one for like a ring. This one was for like a line. And I think we also solved this one, right? I think this was for like a disk. And does anybody remember, did we solve this? I think we did. Yes. And we, for example, showed in the limit of infinite disk, or in the limit of a distance to the disk which goes to 0, we found something like this, the density divided by 2 epsilon naught. And I think this important observation, let me just remind you again. So the Coulomb, or like electric field, change with distance, goes like 1 over r squared for a point charge, and 1 over r for like a line charge, and a constant for planar charge, like this, right? Every time you go from point to line, you increase you decrease the power in the denominator by 1, from 1 over r squared to 1 over r. And if you decrease the power in the denominator by 1 more, you go from 1 over r to constant. All right? Now, okay, let's just solve another example, which will be very important based on our last example, okay? Here's an example from your book. So suppose you have 2 parallel plates, and we would like to determine the electric field between 2 large parallel plates or sheets, which are very thin and are separated by distance d, this distance d, which is small compared to their height and width. One plate carries a uniform surface charge density sigma. Let's call this one plus, and I will call this plate P, plate P. And the other carries a uniform surface charge density minus sigma, this one, and I will call this plate N, as shown in this figure. And the plates extend up and down beyond the part shown, okay? I want to calculate electric field outside here, inside here, and outside here. We have found E is equal to 2. Yes, exactly. We actually have an expression for this, right? For this guy, we calculated the electric field with something with some complex square roots. And when you take r goes to infinity, this whole thing simplified. And it was just a constant sigma divided by 2 epsilon 0, right? That's what we found yesterday. Anybody have any problem with this? I suppose not. So let's use this, okay? So then let's start with this region, okay? Let's start with this one. And I'd like to write, okay, I want to use the superposition such that I'll write electric field from the plate P first, as if there's nothing else. I'll neglect N. And then I'll write the electric field contribution coming from N, again at the same point, neglecting everything else. And I will use the superposition and sum these two things up. Okay, let's start with this point, I don't know, let's call this point A, point B, point C. Okay, like start with point A, or like maybe it's like a region A. Region A. First, let me start with the electric field coming from plate P. Maybe I can ask you, should it be to the left or to the right? So electric field at A from plate P, is it to the left? Left, right? Left, anybody have anything else? Okay, to the left. So it's like something like this. And what is the magnitude? The magnitude, what is it? Right? Yes, right? Sigma divided by 2 epsilon naught. So this is the contribution coming from plate P. Maybe I can write it, plate P contribution. All right, so how about, let's forget about plate P, and now let's think about plate N, but still in the same point. So in which direction should the electric field be? To the right or to the left? To the right, right? Why? Why should it be to the right rather than to the left? What is the reason? It's a negative charge. Thank you. So let me just draw this. Something like that. And this is the plate N contribution. And its magnitude is what? Exactly, its sign is just basically sigma over 2 epsilon naught. So if I sum these two things up, E total is equal to, so 1 minus 1, right? What is the total? Zero. Thank you. Wonderful. Okay. Any questions for this? Wonderful. So let's now think about region B. Now I want to again separate. I just first focus on plate P as if there's nothing else, and then I focus on plate N as if there's nothing, and I sum these contributions up. So first, plate B at point here. Is it the electric field to the right or to the left? Right. Anybody else? Any other guesses? Right, one more right. Anybody wants to increase? I have 2, 3. Right, anybody wants to say left? Seems like no. It's all, so it's like democracy, so everybody says to the right, so it's to the right. And this is, again, the contribution is, right, the same, sigma over 2 epsilon naught. And now I forget about plate P and I focus on plate N. Let's just think about this. Is it to the right or to the left? Maybe I stop playing this game, not to be boring. It's to the right and same magnitude. And this is sigma over 2 epsilon naught. And if I sum these two guys up, okay, last one, like maybe region C. Okay, I think all I need to do is the flip things, right? Okay, let's just not be boring here. So I write this. So this is the plate P contribution to the right. And this is sigma over 2 epsilon naught. And the other one is plate N contribution to the left, sigma over 2 epsilon naught. And if you sum these two guys up, E total is equal to 0. Try to remember these, okay? Try to remember these like sigma over epsilon naught and sigma over 2 epsilon naught. Single plate is half, two plate is sigma over naught, and if you are outside, there is nothing, which is a nice result. And I think you will see problems. Y does not depend on the, what kind of dimension? What do you mean by dimension? So the distance, this distance, right? From A to N. It's basically doesn't depend because we assume these plates are really large compared to this distance. Like if you look at the previous problem, if you have like a finite plate, like this one, it's actually like dependent on the distance as well as the size of the plate. But if you take size of the plate to infinity, the z dependence drops, so you have a constant. And that's actually exactly what happens here, right? Whatever the distance is, the contribution of electric field coming from this guy doesn't depend on the distance to the plate, which is a nice thing. So let me talk a little bit more about electric field lines. And I think I already introduced this a little bit, but let's just repeat some of the things. So 2 things about the electric field lines. I said they emanate from charges or they end at charges. Electric field lines start at a positive charge, they do go out, and they terminate at a negative charge. So the first thing you should pay attention in the electric field lines is the direction of these lines. The direction is out when you have a positive charge, and the direction is in at the negative charge. Okay. The direction is the first thing you should pay attention. And the second thing is the density of lines. Okay. So how many lines do you have, let's say, per unit area? For example, the density of lines in this circle is like, I don't know, 2. But if I draw the same circle somewhere around here, like this, same magnitude, you can see there are like 3 electric field lines. Maybe I can zoom in. So if I draw like a region like here, there's like barely 2 lines, and I draw the same thing here, you can see there's 1, 2, 3 lines. So the number of lines, or like the density of lines, determine or like indicate the magnitude of the field. Okay, and that actually makes sense because field is supposed to be weaker than here, so you should have more lines when field gets stronger. So for example, we can look at more complicated cases, like let's think about dipoles. A dipole is a system of 2 charges fixed at a distance like this, and one charge is positive, the other charge is negative in this case. And like I said, these electric field lines will go from positive like this. They are like, if you zoom in, they are normal at the very small. If you draw a really small circle, they are almost normal to this circle. And as they go, they bend like this. And this bending is due to the other charge. And they just go, curve around, and come back. Okay. For example, if you go this route, it's like straight line. And it's like curving like this, and the curvature is like much larger here, for example. And at any point along this line, if you take the normal, like for example, this point P, suppose you draw a normal like this. That's your electric field, right? That's what this shows. Now, suppose you have 2 positive charges. Now, you again have like for very small circles, it's almost normal to the circle. But as they get further away from the circle or this charge, they bend. But this bending this time is a little bit more divergent. They just repel each other. You can see these lines avoid each other, right? This is the case for 2 positive charges. And finally, suppose one of the charges is bigger than the other one, right? So suppose this is minus Q, a small charge, and this is plus 2Q. the same story. These lines emerge from here and they bend, and or maybe they start from here, they bend and they reach to negative. But the thing you should pay attention, of course, the positive is like out, negative is in, but another thing is number of lines, right? Number of lines here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 lines, whereas in this one, 1, 2, 3, 4, 5, 6. There are twice as many lines as here. So that is done like on purpose to indicate that charge is twice as strong of this charge. So suppose you have like parallel plates. We just calculated this. Like if you have infinite parallel plates, it's like constant electric field. It's in one direction and it's constant. But if you cut these plates at some point, of course, there will be some these like curving at the edges. But generally, we neglect this curving. And the electric field inside is to a good approximation is what we found. E is equal to sigma over epsilon naught. And if this is the direction, this is like x direction. And this is a vector. Any questions about electric field lines? Why do these lines occur? Okay, these lines, let's remember how we got into these lines, right? So initially we were talking about, like back in the first semester, we were talking about contact forces, right? And we were saying that contact forces were like very reasonable. One thing is touching another thing and there is like a force. But if there is no contact, if there is like a force at a distance, it's like a force, like as in Star Wars, that's kind of weird, right? You can't just, you shouldn't be able to move things without touching. And that was the primary reason people came up with electric field lines a couple of 100 years ago. For example, I think it was Faraday. And the picture goes like this. So every charge comes with these electric field lines Faraday introduced. And these electric field lines were kind of like cobweb. They were a property of charge itself. Every charge comes with its own field. And whenever you put a test charge here, this test charge hangs on to this cobweb of the other charge. And you can think of this as like a contact charge. And then that's why they introduced this. But later in the modern science, we know electric fields are more fundamental. Fields are more fundamental than the charges or the forces themselves. Basically, the universe is composed of fields. The field is the most fundamental thing you start with. And then you obtain everything else from fields. There are, arbitrarily complex fields. We'll see some other fields. There's, for example, somebody's talking about gravitational fields, right? Then why don't we have a gravitational field lines? But we actually have gravitational field lines, exactly like this. There's no difference. And there are, if you go to, I don't think this class will take any quantum or quantum field. In that case, the universe is the most fundamental thing in the universe is not particles and charges and mass. None of these are fundamental. The most fundamental thing of existence is fields or like quantum fields. And the quantum fields give rise to everything else you see, or like fields give rise to everything else you see. It's a little bit beyond the scope of this class, but I think it's not bad to hear it. Okay, now once we introduce these like plates and like electric field lines, let's go back to conductors and let's think about the electric field lines in the vicinity of conductors. So first, I want to ask you, if you are given a piece of conductor, I don't know, something like this, and I want to find out electric field inside in the static equilibrium, like here, what is it? 0. Why? Why is it 0? Yes. So, okay, what is the defining property of a conductor? So suppose this is my conductor, and suppose I want to define what the conductor or metal is. What is the number one property of metals or conductors? If I have a charge here, electrons are free. Exactly. That's the key. Free. Free means free, and free as in, I think, free speech. So like they can do whatever they want, kind of free. And if you give tiniest of force on this electron, they are going to move. And if these electrons are moving, this is not static equilibrium. So the upshot is, if there is any electric field inside a conductor, this electric field will give rise to mobility or motion of electrons, and that's like in conflict with static equilibrium, okay? So in the static equilibrium, electric field inside is 0 in any conductor or in any good. Can we say they have loosely bound electrons? Yes, we can exactly say they have loosely bound electrons. That's exactly what it is. But I think the key, I think we mentioned just a little bit, it's actually a complex story. Like it's kind of amazing how like a thing like metals that we see every day can be so complex. But I think I touched on the idea a little bit. It's actually a lot of free electrons. It's just not 1 or 2. It's like a sea of free electrons. So much that it's just like a sea that flows. Okay. Okay. Now we determined that I think everybody agreed that E inside is 0. There's no objection, right? Now I want to ask you the following question. Suppose I put a unit charge here, like let's say I put like an electron or some kind of charge here, E. Maybe I put like a finite amount of charge, let's say, I don't know. Let's not say just 1 E, it's a little bit pathological, but let's say Q. You rubbed, your comb, plastic comb, or like, I don't know, whatever, and then you put some charge here. So what happens to this charge? Okay, maybe I can ask another question. So if I have a charge right inside a conductor, and we know charges come with electric fields, right? I assume this guy is positive, and there's like a charge, right? And now there is electric field inside the conductor. What am I going to do? I put one charge inside the conductor, and now there is like electric field, but I initially told you there is no electric field inside the conductor. What about this? What about this guy? It will dissipate to the surface and neutralize each other from the other parts of the object, maybe. Okay, that's a pretty good and precise prediction. Anybody want to take another guess? So maybe I can tell you, like, okay, if there is like a charge and there is like an electric field, what will happen is like there's like bunch of free electrons here, right? Exactly like you said earlier. There are hundreds of millions of billions of free electrons, right, inside the conductor. And these charges are going to pull to the, pull away from this charge. Or if, like, suppose, like, for the argument, you can do the exact same argument for the opposite charge, but suppose this charge is negative, like negative. Then it is going to pull all these electrons apart. And in turn, all the other electrons is going to pull this guy too. So what will happen is all this charge, okay, of course, this is what I am showing at this moment is not an equilibrium position. So what will happen is the metal itself will delete this charge inside. And exactly like you said, it's going to put it on the surface like this. Okay. It's going to put it on the surface such that, and it's going to do this to satisfy only one condition. And that condition is E is equal to 0 inside. Okay, that's the only result. The electric field would exist beyond the conductor. I think yes, that's exactly true. We will come to this point. So electric field inside the conductor is 0. You're absolutely right. Here is 0. But what I said is like inside conductor is 0. I didn't say anything outside. And outside this conductor, there will be electric fields as if there's like a charge right in the middle, okay? But we'll come to that in a little bit. You're absolutely right. Thank you for this. Now I said electric field inside is 0, right? Now surface. Let's think about surface. Is the surface inside or outside? If I just zoom in right on the surface, I put my charge right over here, and I want to ask, is this inside or outside? How do I know? So why am I asking this? Outside-ish or inside-ish? Why am I asking this? Oh, okay, if this dot I put here, this guy, was inside, I would say electric field inside metal is 0, so I'm 0, I'm done. But in this case, I'm confused. I don't know if this is inside or outside. It's on the border, exactly. So we have to decide what happens on the border. So let's decide what happens at the border, right? Okay, let's say a more general case, something like this, some curved border. This is inside, this is outside. And I want to determine electric field at this point. The first question I want to ask you, is it possible to have an electric field like this? So this electric field has two components, one perpendicular to the surface and one normal to the surface. So one parallel to the surface, one perpendicular to the surface. Right? So yes, exactly. There is no way you can have something like this. If you had this guy would have some parallel component. And this parallel component, if there is any charge here, would move these charges. And that would be not equilibrium. That would not be a static equilibrium. So the metal will not allow anything like this. How about this one? If the force is completely perpendicular, like this, is this okay with like a static equilibrium? Suppose you have a charge over here and electric field is directly like this perpendicular. Is this allowed? So, or the question is this, suppose you have a charge here and you have an electric field on this charge. Can this charge move? And let's say it moves like this, but how can it move? Electrons are only mobile inside the conductor. Once you are outside the conductor, there's no way you can move. It's like a vacuum. Okay? There's no way you can move. If your electron comes here, there's nothing. Your electron cannot come here. It's like, it's not allowed, right? And the upshot is electric field can only be normal to the conductor. And even in the previous, our previous picture, electric field can be only normal, 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 okay? And this is consistent with like a stationary charge on the surface. That's the only requirement to get something like this. Now let's just take another example. Suppose I have a charge, this guy, okay? I want to use this guy. And I put like a spherical shell of metal as outside of this charge. If you like, this is like a, I think we only see the cross section. We are thinking of this to be like a spherical shell. So the first thing I want to ask is the electric field here inside the smaller shell, 0 or, okay, if air exists outside the conductor, what happened? Even in the case of air, air is to a good approximation insulator, right? I mean, if you are not in a very humid day, if you are not like, if you don't have high humidity, and if this is air, nothing happens. Like exactly like the previous story I told you. In the dry summer days or in the dry fall days, your cat will have extra charge because air can do nothing on that charge. But if it's humid, of course, in this case, these charges can bind to like water molecules and dissipate. In this case, we are thinking of like an insulating air, okay? A very dry summer day, if you like. If you put like more and more water vapor, of course, these charges will go and this conductor will be uncharged over time. So let's finish. Let's finish with this example, and I think I will have maybe this conceptual example too. So please go ahead and enter your attendance. This is it. I think this should work. Thanks for the reminder. Now I want to ask you the following. So if you have a charge and a spherical shell, what happens is something like this. Here, of course, you are allowed to have electric field because it's not metal, so it is not in conflict with what we said. But here, you are inside the metal, right? So here, in this region, it's like a metallic region. So electric field should be 0. And what happens is, this metal is free electrons move towards this positive charge. And this first layer is negatively charged. So that if I draw a line like this line, total charge is 0 inside this line. So if this is plus Q, this surface is minus Q. And this is only to cancel total electric field around this region. Now, if there's like minus charges here, there must be plus charges here, right? Total charge is 0 inside this metal. And if you go outside the metal here, this is exactly like there is no metal. Because this is exactly like this electric field lines take an intermission here and emerge from here as if nothing happened. So I want to finish this class with this conceptual example. And it is like this. This is example 14 from your book. A neutral hollow metal box is placed inside 2 parallel charge plates as shown in figure. What is the field inside? What is the field like inside the box? So what is the electric field here? So like based on what we talked, and you are supposed to decide what is the electric field inside here, okay? We can talk about this next